Before we reveal the elegant solution, let's understand the most straightforward method, often called the naive or brute force approach. This technique simply slides our pattern across the text one position at a time. At every single position, it performs a full character-by-character comparison. While simple, you can imagine how slow this becomes when searching through millions of characters. The inefficiency of the naive method comes from repeatedly comparing strings. This begs the question, can we find a way to compare segments of text more quickly? The answer lies in a concept called hashing. A hash function is like a fingerprint generator for data. It takes an input, like a string, and converts it into a single, fixed-size number called a hash value. The power of this fingerprinting idea is that if two strings are identical, their hash values will always be identical. This gives us a brilliant shortcut. Instead of comparing the pattern string with every text window character by character, we can first compare their hash values. If the hashes are different, we know for certain the strings cannot match, and we can skip the full comparison instantly. This hash and compare approach seems promising, but there's a hidden inefficiency. If we calculate the hash for every single window of the text from scratch, we're still doing a lot of work, reading each character multiple times. This would be almost as slow as the naive method. The true genius of the Rabin-Karp algorithm is how it solves this specific problem. The solution is an ingenious technique called a rolling hash. Instead of recalculating the hash for each new window from scratch, a rolling hash allows us to efficiently update the previous window's hash to get the new one. We mathematically subtract the character that's leaving the window and add the character that's entering. This update can be done in constant time, which is the secret to Rabin-Karp's speed. To make this rolling update possible, Rabin-Karp uses a specific type of hash called polynomial hashing. The idea is to treat a string as if it were a number in a non-decimal base system. Each character is assigned a numerical value, and its position in the string gives it a different weight. Just like in the number 253, the 2 is weighted by 100, the 5 by 10, and the 3 by 1. Let's look at the formula this creates. The hash of a string S is the sum of each character's value multiplied by a base b raised to a power corresponding to its position. The base b is typically a prime number larger than our alphabet size. This mathematical structure is what allows us to later roll the hash value efficiently from one window to the next. As you can see from the formula, these hash values could become astronomically large, quickly exceeding the limits of standard computer data types. To solve this, we introduce a modulo operation. We perform all calculations modulo q, where q is a very large prime number. This ensures our hash values always stay within a manageable range, from 0 to q-1, preventing overflow errors. So, the complete formula is mod q. Now, let's walk through a simple example. Let's find the hash for the pattern cab. We'll use a small alphabet where A equals 1, B equals 2, C equals 3. Let's choose a base B of 31 and a large prime modulo Q of 101. The hash is calculated as 3 times 31 squared plus 1 times 31 to the first plus 2 times 31 to the 0 modulo 101. Finishing that calculation, 31 squared is 961. So we have 3 times 961 plus 1 times 31 plus 2 times 1 modulo 101. This becomes 2883 plus 31 plus 2 mod 101, which is 2916 mod 101. The final hash value for our pattern CAB is 88. Now we have the fingerprint for our pattern that we will search for in the main text. Now for the rolling magic. Imagine our window slides from cab to ABD. To get the new hash, we first subtract the term for the outgoing character, C. Then we multiply the entire result by the base b to shift all the characters' positions one place to the left. Finally, we add the term for the incoming character, d. This entire operation is done modulo q. Let's apply this to our numerical example. The old hash for cab was 88. The outgoing character is c, value 3, and the incoming character is d, value 4. The formula is old hash minus old char value times b to the m minus 1 times b plus new char value mod q. This gives us 88 minus 3 times 31 squared times 31 plus 4 mod 101. This single calculation gives us the hash for ABD without rescanning its characters. A crucial detail for an efficient O1 update is to pre-calculate the term b to the power of m minus 1 mod q. This value, representing the weight of the first character in the window, is used in every single rolling step. By calculating it once at the start, we avoid doing a slow power calculation inside our main loop, ensuring each roll is truly a constant time operation. So, the main algorithm loop is simple. At each position, we compare the current text window's hash with our pre-calculated pattern hash. If they don't match, we simply roll the hash to the next position and repeat. This allows us to discard the vast majority of non-matching windows with a single integer comparison. But what happens when the hashes do match? This brings us to a critical aspect of hashing: collisions, also known as spurious hits. A collision occurs when two different strings coincidentally produce the same hash value. While a good hash function makes this rare, it's not impossible. Think of it like two different people having a similar-looking fingerprint. It's unlikely, but you'd need a closer look to be sure. Because of collisions, we can't blindly trust a hash match. Therefore, whenever the hashes match, we must perform a final verification step. We go back and do a direct character-by-character comparison between the pattern and the current text window. This confirms whether we found a true match or if it was just a spurious hit. This step ensures the algorithm is always 100% correct. Let's visualize the two possible outcomes of a hash match. In one case, the character-by-character comparison succeeds, and we found a genuine occurrence of our pattern. In the other case, the comparison fails, revealing a spurious hit. We then discard it and continue our search by rolling the hash to the next window. This two-step process combines speed with accuracy. The performance of Rabin Karp hinges on minimizing these collisions. The best way to do this is by choosing a very large prime number for our modulo, q. A larger range of possible hash values means the fingerprints are spread out more thinly, making it statistically far less likely that two different strings will land on the same value by chance. Similarly, the choice of the base b is also critical. It should be a prime number that is greater than the number of unique characters in our alphabet. For standard ASCII characters, there are 256 possibilities, so a prime like 313 would be a good choice. A good base helps ensure that similar strings, like ward and word, produce distinctly different hash values, further reducing collisions. Let's put it all together. Here is the complete Rabin Karp algorithm. First, we perform a one-time setup. Choose a prime base b and modulo q, and pre-calculate both the pattern's hash and the hash of the first text window. Then we enter a loop. In each iteration, we check for a hash match and verify if needed. Then we roll the hash to the next window and repeat until we reach the end of the text. So how fast is it? In the average and best cases, where a good hash function causes very few collisions, Rabin Karp is extremely efficient. It achieves a linear time complexity of O(n plus m), where n is the text length and m is the pattern length. The initial hash calculations take O(m), and the loop runs about n times, with each roll and compare taking O(1) time. However, there is a theoretical worst-case scenario. If we choose our hash parameters poorly, or if the input is maliciously crafted, we could suffer a hash collision at every single step. This would force a character-by-character verification for every window, degrading the performance to O(n crimes m), the same as the naive algorithm. This is why choosing good prime numbers is so important in practice. Despite this theoretical weakness, Rabin Karp is incredibly useful. It's particularly powerful when searching for multiple patterns at once, as you can check the hash of a text window against a whole set of pattern hashes simultaneously. It's used in plagiarism detection, bioinformatics to find gene sequences, and in network intrusion detection systems to spot malicious data packets. How does Rabin Karp compare to other famous string matching algorithms, like KMP? While KMP has a better worst-case guarantee of O(n plus m), its logic is often more complex to implement. Rabin Karp's reliance on hashing makes it conceptually simpler for many problems, and, as we've seen, exceptionally good at finding multiple patterns, an area where KMP is less suited. In summary, the Rabin Karp algorithm is a powerful, probabilistic approach to string matching. Its true innovation is the rolling hash, which transforms an expensive recalculation into a lightning-fast update. By cleverly using polynomial hashing and modulo arithmetic, it can rapidly discard mismatches, and with a simple verification step, it ensures perfect accuracy, making it a vital tool in computer science.